go on into research now, research and evaluation. Uh, and this section has 16 questions on the exam out of 160 that are scored for you, 16. And I really promote you getting half of those right. I would love to see you get 8 out of 16 right in the research area. And if you get 8 right, that's cool. You're doing great. Because you're going to do so much better in the other areas. So for most counselors, a half right, half of them right is fine. So, but half of them right is good. And so shoot for 8. Now, if you're doing the CPCE, 20 in the CPCE from this section, and you'll need 10 right out of that for half. In the first page there, I'm gonna skip that number 1 and talk about number 2, the quantitative and qualitative. Research that we do can usually be categorized as quantitative research or qualitative. Quantitative is kind of the old line, scientific heavy-duty research from the biologies, the chemistries, the physics, and so on. And typically the research on the quantitative side studied samples and compared it with other samples, control and experimental groups, and they were looking at causality, what's causing what, and usually the heavy use of statistics was part of quantitative. Qualitative research, on the other hand, is much more observation oriented, reporting things out as they are taking place or have taken place. Very little need for looking at causality, like what's causing what. So it's more of a descriptive kind of research. And so there's not a heavy duty use of statistics. You answer different kind of questions in your research, whether you're doing quantitative or qualitative research. There's also now a lot of researchers who are mixing the two up. They are doing quantitative, qualitative in the same research project. They start with one and then they'll switch to the other one. I'll talk about that a little bit later. In the next area, we'll talk about research being inductive versus deductive. Inductive research means that there's been not much done in a research area and you're kind of going in a new spot, in a new area, and doing research that's fairly initially done. And then there's also research that is done for other research that's already been done. And in that case, there may well be hypotheses and theories already out there, and your research that's deductive in nature will typically pose hypotheses out of some theory or some other earlier explanation, and that test for those hypotheses, deductive research. Now, the types of research in item 4, this is the quantitative kind. The first subcategory there is non-experimental, and probably the one that we run into most commonly is called a survey. We do survey research all the time. We're involved in survey research. We probably designed them and administered them. One of the issues about survey research is the people who don't respond, the non-respondents and their characteristics. Let's say that you send out 1,000 surveys around the state, your state, and you get 500 back. So what are the other 500 people like that didn't respond? How different are they from the 500 who did? And how would they skew your data if you had all of them or some of them in your sample? In fact, they may be aliens. I mean, they may be so far out that it could be kind of weird. So you may need to do some follow-ups, and maybe 50% isn't good enough for your research. In some research, they'll shoot for 10% response rate, which is scary, I think, to me. But the non-respondents and their characteristics is the issue here. Descriptive research, the second one after survey, pretty much describing the nature of an event. Comparative research, we do a lot of that, comparing groups or agencies or people or communities or cultures. Correlational, we try to get to the correlational level because that starts giving us some objective evidence of the rate and size of the relationship. And we talked about this with the correlation coefficient, the person product moment. the two tests that you took, the anxiety test and the hostility test, I can correlate them and get some pretty good idea as to their relationship and start posing some questions about what that means. Correlational research, very, very commonly done in the field of counseling and psychology. Ex post facto, the next item on the next page. This is research design that gathers data after the fact, but we're looking for causal connections. But it's kind of a scary process because, in fact, causal comparative research or ex post facto research means that something happens and then you study it. And so pretty much what you're doing is reporting something after the fact. Ex post facto, after the fact, three little Latin words that tell you a lot about the kind of research that is. In the middle of that page, I have an example in the box, and let me read that to you. 2 employment agencies conduct job clubs, and 1 agency job clubs are member-initiated and run, whereas in the other, employment counselors provide instruction and guidance. And examining the job placement rate of members for the past year, you find that the members of the professionally led group had a higher placement rate. 2 groups of job seekers, one is led by professional employment counselors, the other one is not. That group seems to be getting more jobs, those people, than people in the non-employment counselor run group. You might be tempted to say, well, the employment counselors made the difference. You don't know that. This is all ex post facto. You had 2 groups. For some reason, one of them was led by professional employment counselors, the other was not. Could have been the other way around. There was no random assignment of members to one group or the other. The employment counselors were not randomly assigned to one or the other. And so this is all ex post facto, after the fact. Now, you might be inching toward causality by saying, well, but you know, I bet that the employment counselors made a difference. You're kind of guessing, but you know, we call it causal comparative. We'd like to kind of head that way if we could. Let me give you another example of high school kids and working. There's some evidence that kids who work in high school don't do as well as kids who don't work in high school. The ones who work have lower GPAs, class ranks, SAT, ACT scores. Let's say that in May of the school year, you go to the local high school, there's 500 seniors, 250 of them worked this past school year, 250 of them did not. You look at their class rank, GPA scores, SAT, ACT scores. If all of those indicators are lower for those who worked, you might be tempted to say, well, working made the difference. Working caused all of that stuff. You have no idea. It's all ex post facto. It's after the fact. Now, it may, in fact, had an influence, but you don't know that. You'd have to set it up differently to really check that out. I'll tell you how to set it up differently in a bit here. All ex post facto. Now, the next major subcategory is experimental designs, bottom of the page. A true experiment needs 3 things. A true experiment needs a control group, an experimental group, and random assignment to each. Those are the 3 minimum sorts of things to have an experiment. At least 1 experimental group, 1 control group, and random assignment. Okay. Now, on top of the next page, I have another example. 60 college freshmen are enrolled in an English class. 30 are randomly assigned to a 1-hour per week writing lab. The others comprise the control group. End of semester essay examination results are analyzed to see if the lab is writing skills. 60 kids in a class, 30 of them are randomly assigned to go to a writing lab on campus. They spend an hour a week there for a few weeks. At the end of the semester, you check their writing samples of them and the other ones who didn't go. And if in fact the writing scores are different, better for those who went to the writing lab, I would be willing to swear on a smaller stack of Bibles that the writing lab made the difference. I couldn't be absolutely sure. I mean, whoever can be. But if most of those who went there tended to have better writing scores, I would say the writing lab made the difference. Why? I had an experiment. I had an experimental group, I had a control group, and I had all randomization. Now, it doesn't mean some of the control people didn't sneak into the writing lab at night, you know, and got some help or whatever. But, you know, I've got to kind of hope that that didn't happen. Uh, Let me go back to the high school kids and working. Let's say that you personally are very friendly with the school principal, the high school principal near the high school near you. And oh, well, let's say you're married to him. Let's say it's a him, and you're mostly hers in here. You're married to him, the high school principal, and you convince him one night with some wine that you'd like to do an experiment about high school seniors working. You know, you'd like to have, you know, your school year starts in August, go there, and you would say, you 250 seniors have to work this school year, 250 who can't work. And then I'm going to check them out later on. And, you know, and in a groggy state, he says yes. So you do this. So in May, you check out their writing scores, I mean, their GPAs and SAT scores and so on. If all of those were lower for those who work, you'd have an experiment, right? You can be pretty sure that working made the difference here because you've got an experiment, got a control group, and random assignment. So how likely is it that you're going to get this done? Even with a groggy superintendent of your local high school, about zero chance. And so we count so much on ex post facto stuff. You know, stuff happens and then we study it. But so true experiments out in the real world where there are people out there doing their own thing, those things are very hard to do. So most experiments happen, in fact, in labs on campus and medical schools and so on. And, you know, they're good for what we can get, but kind of limited in terms of the content that they can study. I did a 10-year longitudinal, 15-year longitudinal study of career development of kids growing up through school. At second grade, I started with 208 second graders in 4 elementary schools, and I followed them for 10 years. Every 2 years, I would re-interview them through 12th grade. And I wanted to get all the kids in those 4 elementary schools as a big enough sample that would hang around for 10 years. Unfortunately, one of the other things that I ran into was mommies and daddies had a say about who's going to participate in research. So I was limited from about 350 kids to 208, but stayed with them for many, many years. So there are those external exigencies that we need to mess with. Quasi-experimental, the next item down. This is your basic experimental research, except that you don't have randomization. You may have 2 groups, 3 groups, and so on, but you couldn't completely randomize things. So it's kind of like a real experiment, but not quite, so it's quasi. Let's move on to item 5, the qualitative side of research. The first one there is interactive, where in fact you're collecting data, or somebody is, from focus groups, from people you're interviewing, and doing other kinds of data gathering experiences, case studies, ethnographies. Non-interactive research also happens in counseling and psychology, analytical research by historical stuff, biographical, and so on. Some people do only analysis of previous research studies. They do meta-analysis, that's all they do, and so they never have contact with real folks or agencies or whatever. Now, the mixed methods design is mentioned earlier, often done. Somebody will start doing a quantitative project, gathering data, maybe through surveys or tests or inventories or something like that. And then either based on the results or plan beforehand that after that piece is done, they're going to do some qualitative stuff. They're going to do some interviewing of individuals or have some focus groups and so on. So they have a mixed methods kind of design. They do the quantitative first, and then they do the qualitative stuff. Some other specialized research designs and types are listed there. Take a look at those. Single subject action. Action research is pretty much kind of a evaluation type of research that happens. We call it action research in many instances, and I think that's been on the exam. Pilot study, you know what that is. Longitudinal is what I did for my 10 years with my kids. Cross-sectional, uh, research within and between subjects. Again, review quickly, don't spend a lot of time on that. Meta-analysis is a study studying studies. So it's looking at previous studies that have been done in a similar vein, in a similar circumstance, a group of variables, and looking at what came out of those instead of gathering new data. Now, sometimes new research will do a meta-analysis first to kind of see what's the history, and then they'll move on beyond that. But a lot of meta-analyses never touch new research subjects or whatever, and it's only based on. But there's some great information out there. There's been so much research done now in counseling and psychology for the last 30, 40, 50 years that tons of studies done that could use meta-analysis. Internal validity. Now, the next couple items deal with confounding variables, and they're worth at least a couple items. Confounding variables mess up your research. And so if they're around and you haven't controlled for them, you're going to hear about it from somebody, especially if you hope to get anything published with your research results. Now, internal validity, experiments are internally valid to the extent that extraneous variables have been controlled. Okay, they are internally valid. So some of those variables that are possibly confounding you are things like selection of subjects. So where did your people come from? Are they randomly selected from some larger group? Are they volunteers? Did they show up somehow, somewhere without much notice? Are you paying them? I mean, all of these kind of issues might influence a little bit what you end up seeing at the end of your study. Okay, so if you have volunteers, what makes you think that the nature of those volunteers didn't cause the kind of results that you're seeing at the end? So big problem, selection of subjects, big confounding variable. Instrumentation, what makes you think that well, first of all, you're probably measuring something, you're gathering some data in your research project. How are you gathering it? On some kind of a survey or rating scale or test or inventory? How valid is that instrument for your variables? You're studying some variables, you want to measure them. Are you sure that your instruments cover those variables? Do they measure them accurately? What if you designed your own instruments, some rating scales or surveys for your own particular study? Well, how valid are they? How reliable are your own instruments? Lots of questions about the instrumentation possibility here. Confounding variable. Maturation. How old are the people that you are studying? Assuming you're studying people, and how long are you studying them? Now, if you're studying children in grade school, middle school, and you're studying them for more than 2 weeks, they're probably changing right in front of your eyes. If you're studying kids for 6 months, that's going to be a different kid 6 months later than when you started. If you're studying adults, months later, they're going to be different too. Okay, so how about the maturation issue? Is that something to be worried about or not? Mortality or attrition? Well, mortality, you're not interested in because that's death. So if you're studying people, you don't want any of that going on in your study. But if you're studying pigeons or rats or monkeys, you're going to have some mortality, unfortunately. But with people, it would be really problematical. Attrition, you're going to have studying people. Rats are less likely to leave your experiment than people are. Okay, and so why do people leave? Why would they want to plug out? And depending on how long you study them, the higher the attrition rate, reasonable. Why? Why do people get out of studies? Name me 1,000 reasons. Move. The lives change. I mean, the circumstances, whether it's theirs or the family or Who knows, a lover, partner, spouse, I mean, all kinds of possibilities. Uh, and if they kind of leave for whatever reason, and maybe not that kind of nice rational reason, on the normal curve, who are the people most likely to attrition? Who would you guess on the normal curve? The extremes. People who are on the extremes of some normal distribution, but see, they're not at the normal part in the middle. They're at the extremes of some psychological trait, variable characteristic, and maybe that's an important variable characteristic for your study. But they might be either very high on it or very low on something, and they kind of have their own drum they're stepping to, and so on, and will drop out, or it's not that big of a deal, and so on. So you might end up with that kind of richness gone. You might have all those kind of really neat folk adding some richness to your study, departing, and kind of be stuck with that more middle, normal, yuck, vanilla group in it. And it might not be nearly as exciting for your study. Okay. How about experimenter bias? How likely is it that you're really sweating to get some good research done and maybe get a publication? You're up for tenure or something, but you need to have pubs, and so you kind of do a little fudging here and there, and so on. You think it doesn't happen? Yeah, it happens. And maybe even involuntarily, experimenter bias can happen. I mean, you may be primed against it. When I interviewed my little second graders in those 4 elementary schools, and I also had some grad students go out interviewing, I mean, people could say, well, yeah, but you got the answers you wanted out of them. Well, I did. I had a structured interview, and I had some other more objective stuff that I really kind of guarded against that. But I could see people saying that. But then I wasn't the only one gathering the data either. But sometimes you think you're cool and don't have an experimenter bias, and it could creep in anyway. Okay. History. What happens when you're doing the study, and about the middle of the study, something pretty serious happens out there in your community, in the world, in the nation, an earthquake, 9/11, hurricane, something like that happens. Do you think the people are not going to be affected by that? It might be time to do a redo. So what do I do here now? Do I start over? Can I? And minimally, you have to write this into your study that during the project, this sort of thing happened and could have an impact on data. Statistical regression, this is, sometimes we pick people for the study that are kind of at the extreme of on some scales or variables or factors and so on. Well, if you test people again, if they've been on the extremes, what happens? They'll regress towards the middle. And so you better expect that as a result, if that's the kind of folks you started with, because regression toward the mean is a reality that does happen. So all of those are internal validity confounding variables, potentially. I mean, none of them may be there, some of them may, and none of them may be serious enough to be really concerned, but if you're not concerned about them, probably somebody else will be. External validity, the next item. Most of us study research in samples, for samples of people or groups and so on. But the intent is to generalize those samples beyond, the research beyond the sample that we're studying. And you can't do that again unless you've taken care of some confounding variables. So an experiment is externally valid to the extent results may be generalized to others. Selection of subjects. If you expect to generalize any of your data from your small study to the population or school community or something bigger, and you didn't have randomization of subjects, you can forget about that. Nobody will believe you if you do, because it's a really scary thought. So selection of subjects, ecological validity. Sometimes we do research in such a unique circumstance under such different conditions or unusual parameters that it won't generalize. There aren't other ones like that out there, or not very close like it out there. Or even like military research, can you generalize that to the civilian world, or vice versa, and so on. So there's questions about ecological validity. Subject reactions called reactivity. Let me tell you a little bit about Hawthorne. Western Electric Company in the 1920s in Cicero, Illinois, was trying to make more and more telephones. Telephones were getting to be pretty big then, 1920s. So they put a bunch of people in a room like this and increased their lights, and their performance went up. They made more telephones. They added music, performance went up. They lowered the lights, performance went up. It didn't matter what they did with these folks. So it was the attention they were getting, and the plant that they were doing this experiment in was called the Hawthorne plant. And there's where Hawthorne came from. Demand characteristics, these are the clues, the information, the innuendos, all the other information you have about a research project that can influence you in terms of your performance. In Psychology 101, where most of you were in undergrad, I assume you took Psych 101, a lot of you did, you had to do some kind of experiment to get credit on. Some professor was doing some experiment, and you talk to the other students about, so who's doing something interesting out there? And you've got to get some credit, and it's a pain in the butt, and so on. And you start talking to each other about the project, and the do's and don'ts, and the nice things and the uglies, and so on. And that all influences you. These are demand characteristics. Experimenter bias shows up again. A guy by the name of Rosenthal, not this Howard guy, spent a lot of time studying that, and he called it Pygmalion effect. So we have kind of a layered set of issues there, Pygmalion and Rosenthal and experimenter bias. Placebo. Placebo typically has meant that little inert sugar pill that was given to control subjects not getting the real medicine. We can also talk about placebo as a control in a regular experiment. For example, let's say that I am trying to determine sixth graders' reactions to a mildly violent videotape. So I've randomly selected, a classroom of sixth graders, and I've got a control set of sixth graders. And my experimental group, they see this little 5-minute video, and they do a 10-item questionnaire about that. Now, my control sixth graders should not be out on the playground having fun. They should be in another classroom watching another video that doesn't have the violence clip. That's a placebo control. So it's an identical kind of thing, except for that key little thing that I'm studying. Novelty and disruption effect. When you join an experiment, sometimes it's kind of neat and exciting. You're finally getting some attention from somebody, and you're all exuberant about that, and you start responding in certain ways. And then after a while, it wears off, and maybe it's starting to disrupt your life. And you're walking across campus, like University of Wisconsin, in the middle of winter in January, just to get shocked in a lab somewhere, and all of a sudden you kind of develop an attitude about that. And you find out that the guy that is shocking you was married. You thought he was kind of an eligible grad student, and it all kind of goes to heck. So disruption happens. So all of those are confounding variables, and that's not all of them, but these are the most important ones. So worth keeping in mind if you're doing that kind of research. Again, any one of them would be a great question on the exam. Levels of measurement, let's review those. And the nice thing about the levels of measurement, if there is a nice thing, is that they're the same as they were back when you were in the 6th grade. And so, assuming you've got some memory at all, it's not a big deal. Nominal means you name things. Nominal level of measurement, you put things in categories. Nominal comes from the Latin word nomen, to name. So you name men versus women, freshmen, sophomores, juniors, seniors. You've got Humvees, you've got sedans, you've got whatever kind of car. You can put things in categories. That's nominal data. When you have that kind of nominal data, the categories, the best statistical technique for that is called the chi-square, and we'll talk about that in a while. The next level of measurement is ordinal. Ordinal means you can order the data. Anybody who gives a test or an inventory rating scale thinks that they can order people's results from top to bottom, high to low, low to high, whatever. Ordinal data, we can order stuff, okay? And that's how we deal with the data. The next one is called interval. Not only can we order it, we say that the intervals contain the same amount of that psychological trait or characteristic. So not only do we order it, top to bottom, high to low, but we say that each of those little markers contains the same amount of that quality of variable characteristic. And to me, that's kind of a scary part, to be able to do that. Some of you maybe have seen the MMPI profile sheet. It's been a few years since I have, but it used to have all kinds of, like, from standard score 20 on the bottom to 80, tiny little slices of schizophrenia and bipolar and all kinds of other maladies on there. And it's like we could slice these abnormalities into these little pieces, and that they're actually true, these slices. I mean, that's the thing that confounds me a little bit. But we do that, and most folks live with that kind of interval measurement. So ordinal and interval are very commonly done with our instruments, our tests and inventories, ordinal and interval. And either one will let us use certain kinds of statistical techniques. The t-test, the analysis of variance, we're going to talk about. So either way, they're cool for that. Now, the next kind of measurement is called ratio scaling. And let me give you an example of a ratio scale. Let's say that I had a new scale inventory called an anxiety scale, and these were the possible scores on it. On a ratio scale, somebody with a score of 80 is twice as anxious as the 40. The 60 person is twice as anxious as the 30. The twice as. Do you know anybody who was 1/3 as introverted as you, or 1/2 as bipolar, or 1/3 as outgoing? We don't know that. With psychological traits and characteristics, you need to have a true zero. On a ratio scale, you have to pose or posit a true zero. There is none of it. Some people don't have any of it. Well, that's cool for height, for weight, for measurement, length, and so on. Maybe distance, time, and such, but not for psychological traits. So ratio scaling is pretty much out of our category, out of our world, unless you happen to be doing maybe reaction times or brainwave patterns or something, and some kind of research. But ordinarily, the ratio doesn't work for us. Okay, sampling, the next item. I've talked a little bit about the random sample and other things. Let me go a little bit more in depth about sampling. And I'm going to stay with my school example. Let's say that there are 2,000 kids in a high school. I want a random sample of 200 of those kids. Random means what? That everybody in the 2,000 has an equal and likely chance to get into the 200. I can do it multiple ways. I can put all 2,000 names in a hat and draw out the first 200. That's going to be my random sample. I can go to a computer program. I can number all the kids from 1 to 2,000, and then the first ones that come up, 200, I can pick on my computer program. Lots of ways to do that. The nice thing is that about that 200 is going to tell me everything I need to know about the 2,000. If you do a random sample, but if you pick you know, the first 50 kids that walk down the hallway between classes as your sample, you're in trouble. You're not going to generalize anywhere. But randomly to pick 200, even out of 2,000, will tell you so much about the kids in that school. So that's what I'm going to do. When I realized that I also have subgroups in my school, I've got African Americans, I've got Hispanic Americans, I've got white type folks, uh, I've got blacks and I've got Hispanics and I've got whites. If I know that I have these subgroups, I need to make sure that those subgroups are represented in my random sample. Then I would have a stratified random sample. That's even better than random, okay? If I know the proportion of these subgroups in that school of 2,000, that would be even better. Let's say that 30% of my kids in the high school are black and 20% are Hispanic and 50% are white. I need to have the same percentages, hopefully, in my random sample. I would have a proportional stratified and random sample. Doesn't get much better than that. Except you can have an Asian American come up to you afterwards and say, you don't have an Asian American group. Well, what I would do if I knew what I was doing, I would figure out the percentage of blacks in the school, Hispanics, then this would be all other. Everybody else would be in with the whites, the Asian Americans, the Native Americans, and whoever else. So everybody would have a chance to be represented. One of the problems with small ethnic groups, that if you pick one or two people for your study, they may be identifiable almost. So you've got to be careful that you don't violate some confidentialities by figuring out a small little 5-person Asian American group and then picking one person from there. So who's going to figure out who's the Asian American in the study now? So, well, I would look at this. I would look at the size of my major subgroups, like blacks, Hispanics, and whites. And then if that comprises 90% of the school population, that means everybody else, Native Americans, Asian Americans, and whatever else is 10%, I would fold them under the white, the largest subgroup. And they would have just as likely a chance to get in as anybody else. I mean, I'm still going to pick whoever comes in. I can, assuming that they're identifiable some way, I would keep pulling them out of the hat and they would have their ethnicity on there. And once I got up to 30 blacks or whatever, then if the next block pulled out, I would put it back in and choose somebody else. So I would only pick up to 30%. I can't, because I could end up with a very, very unwieldy sample that wouldn't be appropriate. So. Okay, so that's sampling and some of the suggested subtypes. Let's go on to cluster sampling. Cluster sampling is basically group sampling. And you can do this randomly as well. Let's say that you have an elementary school with 3 first grade classrooms, 3 second, 3 third, 3 fourth, 3 fifth. You could randomly pick one of the 4th grade classrooms, one of the 5th, one of the 3rd, one of the 2nd, and so on. However, you have to make sure that all classrooms in each grade level are identical. So let's say in 4th grade, you pick a classroom randomly. If all the special 4th graders are in that classroom, it's not random for 4th graders. Or if none of the special kids are in there, they're all in the other 2 classrooms, but you didn't pick them, you're not random for 4th graders. So all 3 4th grade classrooms have to be comprised pretty similarly in terms of kids, then you randomly pick one of those. Cluster sampling. Sometimes you don't care about random at all. You do what is called purposeful sampling, okay? You're much, much more concerned about very discreetly, openly picking people or couples or families or cultures or groups to investigate rather than take a random mix of some kind, okay, purposeful sampling. Um, some other samples out there are sample of convenience. A sample of convenience is scary. My example is this. You get permission from a local elementary school principal that you can give a 5-item little survey about some current local issue to kids in school. And he says, well, you can't do it during school time. You can only do it before the kids walk into the building. He said, all right, it's fine, that's cool. So you go sit on the front steps of the building, you know, at 6 in the morning, and the first 50 kids that come to school, you have them fill out this little 5-item survey about something. That's a sample of convenience. Who are you going to generalize that back to? You know, maybe the first 50 kids that come to school, I mean, who are these kids? They've got an early class, these are elementary kids. My guess is that they're the kids whose moms and dads work the furthest away, drop the kids off an hour early, then they drive to Colorado Springs from here or wherever, so they can be at work on time and the school babysits the kids. So those are the kids I'm getting. So I'm going to generalize that to these kids. I can't generalize it to the school. So these are scary samples. Samples of convenience are, you know, people who walk in or who kind of show up and so on, and you gather data from them, but the generalizability is really, really scary. Well, the other scary one are the volunteer samples. You walk into the local mall, wherever you live, and there's this lonely person with the long clipboard would love to ask you 2 questions. You know, and some people do that, and they spend some time answering questions. And again, who does this person, agency generalizes results to? I don't know. Volunteer samples are scary, about as scary as samples of convenience. So, and we'll talk about them a little bit more. Questions so far? Everything understand? You guys all look alert and alive and not excited, but alert and alive. Cool. Sample size. Sample size, when you're doing survey research, 30 is really the minimum. That's correlational, ex post facto, 15. Experimental or ex post facto. So if you've got groups, subgroups, control groups, experimental groups, you need to look at least 15 in each one. And that's to have your statistical techniques make any sense. If they're smaller than that, you really run a risk of not showing anything, even if you have it. Surveys is 100, they have their correlational is 30. Stat analysis is of 2 kinds. The first 2 kinds, and then there's another set of kinds on the next page. Descriptive or inferential. Stat analysis, descriptive or inferential. Descriptive means sometimes called summary. Almost every time we gather research data from a sample of any size kind, we will do some summary descriptive statistics. It might be mean, standard deviation, range. It could be frequency counts, pie charts, bar graphs, and so on. We want to describe the statistics to people, the group that we've studied. That's your descriptive statistics, okay? Typically, when we study a sample, we also want to generalize it back to a bigger population. We pull a sample out of a population, we want to generalize back, and when we do that, we go into inferential statistics. So we study a sample, but we want to make inferences, infer to that larger population the sample came from. And when we do that, we can use different kinds of statistics, like the t-test, the analysis of variance. We'll talk about those. Now, the other combination of samples are parametric versus non-parametric. Para means 2-sided. So when you've got a parametric sample, the data it generates results in a normal curve, in a 2-sided normal curve. Okay, and that's really valuable to know, parametric statistics. Now, the other piece that goes along with that, besides normal curve, is something called homogeneity of variance. Homogeneity of variance. So you are studying the sample, and you figure out the variance of the sample. There's also a population you're concerned about, and there's a strategy to figure out the population variance. You need to make sure that they are homogeneous generally. So if you have homogeneity of variance between your sample and the population, and the data is bell-shaped curve, then you can use parametric statistics. Now, let me tell you that this homogeneity of variance criterion is way overrated. I wouldn't spend a lot of time and energy on remembering homogeneity of variance, but do remember that normal bell-shaped curve. Without that, you can't do a lot of statistics. So you're looking for parametric statistics to use. It needs minimally the normal curve and hopefully also homogeneity of variance. Okay. Now, when you don't have that kind of a normal curve in your data, you've got to skew this way or that way or other kind of data, then you relegate it to non-parametric statistics. And the bad thing about them generally is that they're not as powerful as the parametric statistics. So they're not as likely to show you having some significant results as do parametric statistics. Now, the difference is fading, it seems, over time as people are doing more research about them. But even so, there's a general feeling that parametric ones are the ones to use if you can. Okay. We'll talk about some of the non-parametric ones later after we do review the parametric statistics, the t-test, analysis of variance, and so on. Now, let me talk about variables because they're going to be kind of at the heart of our next conversation for a while here. There are two kinds of variables out there that you need to know about. One is called the independent variable, and the other one is the dependent variable. The independent variable is misnamed. It is not independent. Somebody's fooling us. Independent kind of implies that, you know, it's out there, it shows up when it wants, and, you know, bugs us when it wants to, and so on. In fact, we control the independent variable. We decide if it's in our study or not. Okay? So it's very much under our purview, the independent variable. The dependent variable is the one we measure. If you're doing a research project of any kind, you probably have to have something measured, some results, some treatment measured, and so on. Well, that's the dependent variable. Now, you may have more than one, and you may have more than one independent variable in your study, very likely, but at least one of each minimally independent and one dependent variable as well. My example in a box on 237. The effects of three kinds of therapeutic technique, all of those are independent variables on anxiety. So I'm doing a study, doing some kind of therapeutic study with three kinds of techniques, and I'm measuring people's anxiety at the end. So what I'm measuring is the dependent variable, that's the anxiety. My independent variables are the three kinds of treatment that I'm using in my study. I could have said 5 times or 20 times or 50 times. Okay, under my control. So independent and dependent variables. Now, under that box, the independent variable is also sometimes called stimulus, predictor, or experimental variable, and the dependent is sometimes called response, outcome, or criterion. And we'll see some application of that a little bit later on in this section. Research questions and hypotheses. Research questions are very, very good to ask in a research project. You don't need hypotheses necessarily. Research questions are fine. A couple examples I have here. The first one, is there a relationship between disciplinary practices and leadership style for men in the military? And that sounds to me like a correlation kind of question, that maybe I'll need to use a correlation coefficient. of some kind to figure that one out. The next research question, is there a significant difference in the mean number of client contacts between public and private counseling agencies? Kind of an interesting question. So if that's the case, that sounds more like a t-test, kind of a statistical technique used there for that one. Now, if we don't use research questions, we likely are using hypotheses to test in our research. The most common hypothesis we use is called the null hypothesis. Null means no. When you pose a null hypothesis, you are expecting no differences between 2 or 3 or 20 groups, okay? Top of the next page. There are no significant differences in final academic grades, GPA between boys and girls finishing the 10th grade. I have no idea whether boys will be higher than girls or girls higher than boys, and so I pose a null hypothesis that will be no difference. I don't even know if there's going to be a difference. Okay? I'm expecting no difference, in fact, with that kind of hypothesis. Now, if I had studied the literature about boys and girls in 10th grade academic performance, I know that girls always have higher GPAs at the end of the 10th grade than boys. I'm overstating that probably, but I could have had a different kind of hypothesis to test. I could have tested not a null hypothesis, but an hypothesis that said girls will have a higher GPA than boys at the end of the 10th grade, and test for that. What happens when you do that, and it's not, irrelevant. Girls higher than boys, boys higher than girls. This is a two-tailed test. A null hypothesis is two-tailed. But if I say a directional hypothesis, girls will have a higher GPA than boys, I've ruled out boys being higher than girls. It becomes a one-tailed test. And I need a bigger difference in my data to be significant, statistically significant. So that's the difference between null and directional, okay? Whether you need it or wanted that or not, that's where it is. Now, I could even have another alternative, which means that there will be a difference, but I have no idea which way it's going to go. See, the null hypothesis says there will be no difference. Then I said, no, the girls will be higher than boys, or I could say the boys higher than girls. But the my third example is the GPA of boys and girls finishing the 10th grade will be different, but I don't have any clue which way they're going to go. I just expect a difference. So those are all, those second two are alternatives to that top one on that page. Okay. Okay, we're going to talk about something called statistical significance next. And this doesn't get your blood pumping. I don't know what will. Statistical significance is something that researchers are asked to determine, to identify before they analyze their data, maybe even before they do the study. And instead of waiting for you to have all of your data and some analysis done and say, well, I'm going to pick 0.05, or I'm going to pick 0.01 because it beats 0.01 or whatever. So you have to set this in advance according to the research ethics books. Very common kind of a significance level is 0.05. 0.05 means simply that I am willing to live with error, mistakes, abnormalities, strangenesses in my data if it doesn't happen more than 5 times out of 100. I'm willing to live with errors, mistakes in my data if they only happen 5 times out of 100 or less. If that's the case, then I'm going to say whatever results I have, I'm going to say are meaningful. Okay? Now, if that's too loosey-goosey for you, it's way too liberal, we can go 0.01. So if the mistakes happen only 1 time out of 100, that means if you did the experiment 100 times, 1 time, you're pretty sure you're going to have some error in your data, and you're going to make a mistake either accepting or rejecting hypotheses. You can be even more conservative and go 0.001, 10 out of 1,000. I mean, that's right next to godliness, I think. So, okay, so 0.05 is a good conservative, starting point for most research data. And, but there's always the error possibility of making a mistake and either rejecting a null hypothesis or not rejecting when you should, okay? And those we're going to get to called type 1, type 2 error. But before we get to that fun part, I'm going to take you through item 18. It's a long example, but we're going to use this for several of the next few items in the book. The example, assume you are the director of a large counseling agency which employs 24 therapists, 12 of whom are men and 12 are women. You are curious about the self-esteem level of clients who complete therapy and wonder if there's a relationship between gender of therapist and client self-esteem. For 6 months, you randomly assign clients to all counselors. As these clients terminated, their self-esteem was measured using a standardized test. After all the clients who began therapy during that 6-month period of time were terminated, you began your stat analysis. You're the agency director, large agency, 24 therapists, 12 men therapists, 12 women therapists. Obviously all very kind of clients there. Somehow, somewhere, you read, heard, went to a conference, and somebody reported on the possibility that maybe gender of therapist influences the amount of client self-esteem at the end of therapy. Men's clients are different than women's clients in terms of self-esteem. And you heard that, you're wondering about that, puzzling about that, because you've got 12 therapists of each gender, you think, I could check that out. You could do something about that. Your null hypothesis underneath that box, there is no significant difference in mean self-esteem scores of terminated clients. You know that you're going to play it safe. You have no idea if there's going to be a difference or which way it would be, but that's basically your starting point. So your significance level is at 0.05. You're going to keep it there. Then the question becomes, how likely is it that you're going to get a result that will meet your expectations? You've got male therapists, you've got female therapists, you've got client self-esteem down here, client self-esteem down here. So the client stuff is what we're measuring here. We're not measuring anything up here. When you have two groups like this, your statistic of choice is called the t-test. T for 2, only for 2, no more than 2. T-test. T works for 2. Long involved formula, lots of steps, and back in the old days, 50 years ago, people were doing them by hand. I remember that. Probably not 50 years ago, but I still remember doing it. And anyway, you end up with a t-value, a value for t at the end. That's kind of your bottom line, t-value. You've got two groups. You're looking at their client self-esteem scores. You get a t-test. The bottom line is the t-value. Again, in the old days, there was a table of t-values. A guy by the name of Student found this out, designed it. On top, you've got significance level, 0.01, 0.001, 0.01, 0.05, and so on. On this side, you have something called degrees of freedom, which you don't need to know about. That won't be on the exam. But you try to figure out the degrees of freedom in your project, how many variables you have, and so on. And you take that t-value you generated to the right spot in the table, like here, 0.05 is our significance level. If your value is higher than the value in the table, you have significant differences. Isn't that cool? And your null hypothesis says no differences. What do you do with that old null hypothesis? You reject it, right? You reject that null hypothesis. You would reject the null hypothesis. The problem is you're going to be wrong 5 times out of 100. So rejecting the null hypothesis when you shouldn't is called a type 1 error, an alpha error. Your data says you do reject it in this case. You reject it and you're fine. But again, 5 times out of 100, you're going to make a mistake and reject it when you shouldn't. So rejecting it in an alpha error, and you will make that error. But there's also a flip side to type 1 error. It's called type 2 or beta error. Beta error means you don't reject the null hypothesis when you should, okay? You don't failure to reject the null hypothesis when there is in fact a difference. You're likely to do one or the other, at least to some extent. The higher you set your significance level, the more likely you're going to do the other error, and vice versa. So there's a relationship there. So, type 1 and type 2 error are fairly esoteric concepts, I think, in this whole thing. Now, I don't want you to spend a lot of time trying to figure them out necessarily, but let me give you another example to kind of solidify the differences. And I use a jury example for this. Let's say that you're the jurors in a murder trial. A man accused of killing someone is on trial. In a court of law in the United States, we generally assume innocence until guilt is proven. So the null hypothesis in a court in the United States is a null. No guilt until it's proven. Well, let's say that that's holding for this man. You're the jurors, you hear the evidence, you go back to the jury room, and you come back and you commit a type 1 error. What are you telling them? Okay, you throw out the null hypothesis of no guilt. You say you are guilty, but you're wrong. It's a scenario. So you say you're guilty, but in fact the man is innocent. Okay? Type 1 error. What if you come back and you commit a type 2 error? You say you're innocent, but in fact he is not. You commit another error the other side. You commit a type 2 beta error. You are innocent, but the man in fact is guilty, stands up and cheers and hugs his attorney and waves at you, the jurors, and struts out of the courtroom. He said he's innocent, but he's guilty. That's the type 2 error. So which way do you want to make that mistake? Would you rather err on letting a guilty one get off or hanging an innocent one, which we seem to do in some level of measure these days? So, okay, type 1, type 2 errors. Let's go back to our example. I'm still working on this, and I'm thinking about that, and my clients and their self-esteem scores, and male and female therapists, and so on, and I'm thinking, maybe is it possible that the level of training of my therapist could make a difference in terms of self-esteem of clients? I have LPCs in my 20 counselors, 24 counselors. I have MSWs, and I have PhDs. Maybe the level or kind of training is influencing client self-esteem. I'm still interested in client self-esteem. Okay. But see, now I would put it here. Something like this. And maybe this is the big issue. And now what do I do with this in terms of statistical technique? Can I use a t-test? I cannot. I have more than 2 groups. And so I need to use something different. And but before I tell you the different one, let me ask you, so what's wrong if I do a t-test here, I do a t-test there, and I do a t-test there? Is that okay? Do 3 t-tests instead of... Well, the problem with this is that this is very research unethical. You send that data into a journal to be published, the editor will see that and they will send it right back and say, use a different kind of stat technique here. I'm using 3 t-tests here, these, and these. The more statistical tests that I use, the more likely it is something will show up significant. So I have to use the minimum number of statistical tests with my research data, the minimum. And it's not t here. I can't use 3 t-tests. This is called experiment-wise error if you do this. And just a no-brainer for most folks who are in the business. You stay away from that. So we've got 3 groups here. I can't use a t-test. My choice for analysis then is a one-way analysis of variance. One-way analysis of variance. And this is the first of 3 kinds of analysis of variances I'll talk about. One-way analysis of variance for more than 2 groups. You end up with an F value. The bottom line is an F for all kinds of analysis of variance. You end up with an F value. There's another table. You can take it to the table. Or now when you run these analyses, the computer will tell you whether you're significant for your t-test or your analysis of variance at the 0.05, at the 0.01, at the 0.001 level. So it all happens instantaneously in a nanosecond. Okay, so one-way analysis of variance is your choice here. Well, I'm thinking about this as agency director, and I really like that gender concept I heard about, and I don't want to get rid of that. And so I'm going to add that back in here. I'm going to add, and let's see, we're testing for self-esteem. Okay, somebody tell me, what kind of variables do I have listed here on the board right now in terms of independence and dependence? Anybody? How many of each and what kinds? Okay, type of degree, LPC, MSW, PhD is an independent variable. Okay, I agree with that. Gender is an independent variable. Dependent. This is what I'm measuring one thing, self-esteem, and that's a dependent variable. So I have 2. So how many independents do I have altogether? 2, 5, 2 times 3 is 6. Anybody? I have 2. One is at 2 levels, gender, and 1 independent variable is at 3 levels. So when I look at that, well, one of the nice things about doing 2 independent variables is you can look for interactions. Maybe master's level trained therapists, these 2, they end up with clients lower in self-esteem than doctoral male clients end up with higher self-esteem. Maybe it's the opposite for women therapists. Maybe the master's level women therapists end up with clients with higher self-esteem, but it's lower for PhD women therapists and their clients. You've got an interaction between both gender and training or degree. It's an incredible piece of information to find out. And you can't do that with a t-test. You can't do it with a one-way. You can only do it when you've got at least 2 independents going on, and perhaps more. And this is a pretty simple, straightforward scenario here with the 2. One at 2 levels, one at 3 levels, okay? This is called a factorial, a 2x3 factorial analysis of variance. I'm going to just say ANOVA here. A 2x3, 1 independent variables at 2 levels, 1 independent variables at 3 levels. So I have a 2x3 factorial analysis of variance. One of the other things that I'm thinking about, I have some ethnicities in my therapists. I've got some Black therapists, I've got some Hispanic therapists, and I've got some white therapists. Is it possible that client self-esteem is related to the ethnicity of my therapist? Not out of the possibility realm, is it? So, I want to add this. What is this? This is another what? Another independent variable that I'm thinking of adding. We'll call it ethnicity. And so if I do that, I then I have a 3 by 2 by 3 factorial analysis of variance. Okay. Now, having 3 independent variables makes your interactions a little bit messier, a little bit more complex. But with these number of levels, 2 and 3 and 3, it's still a piece of cake versus 6 here, 10 here, and maybe 4 here. Some research projects are incredibly bulky in terms of their number of variables. So this would be a 3 times 2 times 3 factorial. The problem is I would need about 600 therapists to pull this off, okay? And I only have 24, so I can't do this third independent variable. I would need 15 male LPC Black therapists, 15 male LPC Hispanic therapists, and so on. I run out of therapists really fast. So we're going to drop this third independent variable and stay with a 2 by 3 factorial at this time. Okay. Now there's one more kind of factorial analysis of variance. I am also interested in locus of control. One of the things I think that counselors do often with their clients is try to get them to look at who's controlling their stuff. Many clients come in and they say, well, these things are happening to me. They're kind of at the mercy of this, that, and the other. I think a lot of what we do is to try to establish kind of some self-empowerment, getting them to be in charge of their own locus instead of giving it to other people and things and circumstances to control them. So I'm going to see if clients at the end of therapy have had a change in their locus of control. So I'm going to measure for that also, okay? So what is this? It's another dependent variable. I'm measuring 2 things now, self-esteem and locus of control. And when I do that, when I've gone from 1 to 2 or more, it becomes a multivariate analysis of variance. Multivariate, MANOVA for short. Okay, MANOVA, multivariate analysis of variance. And let me get rid of this one. This is our third kind of analysis of variance. We had the one-way, we had the factorial, and now multivariate. When I have 2 or more dependent variables, I'm going to measure their anxiety also. So now I'm going to measure 3. I've got 3 dependent variables. I could measure 10 dependent variables. Of course, if they want to go home, whatever, they're going to need to let them out. But in any case, our 4 kind of analyses are t-tests for 2 groups. One-way analysis is for 1 variable, but 3 or more groups. 3 or more groups, one-way analysis of variance. When I have 2 independent variables and only 1, if I have 2 or more independent variables and only 1 dependent, that's your factorial. When you have 2 or more independents and 2 or more dependents, that's multivariate. So those are your options, okay? And in all the analysis of variances, you'll end up with a F value that will be kind of your bottom line value. Okay. Questions at all about? Let me get one more shot at you folks in terms of complexity called analysis of covariance. Once in a while, when we do research and we find out something about the individuals via a pretest, typically, that the information could influence how they interact with the principal variable in the study. I need to then make an adjustment of scores before that happens. Let's stay with the same example. Let's say that I'm the agency director. I've got all of these folks, and the men get very random clients. The women therapists get random clients. Let's say that on a pretest of self-esteem that I would give them, let's say that the men pretest score is 91 and the women clients pretest score, the women therapist clients, all the clients scores is 97. Okay, this is on a pretest. And one of my issues is trying to see if gender is related to self-esteem scores of clients at the end of therapy. And my male therapists end up with clients already starting at a 91, low score on self-esteem. My women therapists end up with clients starting out with 97. Oh, what's my problem here? I am really disadvantaging my male therapists, aren't I? I mean, if I'm interested in self-esteem going up, hopefully in both groups, my male therapists, their clients are way down on self-esteem versus my women therapist clients. I can't go ahead and do an analysis on the post-test. Let's say that on post-test, these go to 101, and let's say on post-test, these go to 102. If I did an analysis, I could do it on the 101, 102, but it would be a little bit spurious, wouldn't it? I probably need to do it on the difference between these two. So what I'm saying in terms of analysis of covariance, if I know something based on a t-test in advance, I may need to adjust the scores before I run my analyses, my factor or my multivariate and so on, factorial or multivariate. Another example, let's say that I am studying my fourth grade math classrooms again. I've got 3 of them. I'm the principal in the school. I went to a conference in July somewhere in the country, and I came back all excited about teaching math different ways. So classroom A, I am going to tell the math teacher, I want you to teach this way in math. Classroom B, I want you to teach this way. Classroom C, this way. I'm going to find out then in May which math teaching technique is the best by giving them some standardized tests. In March of the school year, I find out that the mean IQ of kids in classroom A is 101, in B it's 114, and in C it's 102. Mean IQ score of the kids. I find that out in March. So I have a problem here. I'm trying to see which math technique is the most effective in the 3 classrooms. And yet I have a classroom that's mean IQ is 114. I mean, incredibly high and different than the other 2. Don't you think that math technique's going to win out? Probably. And so I'm really disadvantaging the whole system by doing that. And when I analyze this, I'd probably not even throw B into the formula. I'd look at A and C and see which of those math techniques are the best, given that you're dealing with pretty much a sample of kids that are similar in intelligence. Analysis of covariance. So you make that decision, then you go ahead and you run your analysis. Number 26, your post hoc multiple comparison test. I've been saying that you end up with an F value. You don't know which of those where the differences are. If you have significant differences, are these 2 significantly different? Are these 2? Are these 2? Or are these 2? You've got to do the post hoc test to figure that out. Things like Chaffee's, Tukey's, Newman-Cool's, Duncan's. Don't memorize the specific one, but know something about post hoc tests. for that one. Non-parametric test on the next page. The Mann-Whitney U-test is a substitute for the t-test. When you have two groups and you look at their scores and you find that they're skewed, they're going all over the place, they're not parametric, you can't use the t-test. This would be your substitute, your Mann-Whitney U-test. Wilcoxon signed rank test. There is something called t-test for pairs. Sometimes we pair people and get one score. Sometimes we have the same person get two scores. T-test for pairs, we can use it if we're normally distributed. But if we're not normally distributed, we have to use something like Wilcoxon signed rank test. Kruskal-Wallis, let's say you've got 3 or more groups and you look at the scores and you've got skew all over the place and so on. You can't use the one-way analysis of variance we've talked about. You'd have to use a Kruskal-Wallis, which is a non-parametric one-way analysis of variance. Chi-square is our statistic of choice when we have nominal data in the box up on top of the next page, and the null hypothesis starts on the bottom before. There are no significant differences in number of boys and Jeans who wear schools in high school. And you've got your contingency table, yes, no, boys, girls. You would need to observe, first of all, and get some numbers from your observations. Then there will be some expected frequencies that you would generate by formula, and then look for the difference. Solomon 4 group design is a great design that is used when you think your pretest will influence how people interact with your treatment. Sometimes we give people, you know, a pretest that gives them like lots of information about what they're about to get in the experiment or whatever. And if you're worried about the impact of that, the Solomon 4 group design is excellent for that. Group A gets the pretest, gets the treatment, gets the post-test. B gets the pretest, doesn't even get the treatment, gets the post-test. C, no pretest, yes treatment, yes post-test. D doesn't get anything but the post-test. You can see if the pretest by itself made a difference, if the treatment by itself made a difference, if a combo of them made a difference, or if nothing made a difference. Very wise Solomon design. The problem is you need a lot of folks for this. You need at least 60 people, 15 in each minimally. So it's a lot of people, a lot of money, a lot of expense, a lot of hassle to do it well, but worth it. Multiple regression. This is now use of the correlation again. And this is dealing with variables, independent and dependent variables. Take a look at that and you'll see how they really match up nicely with like the factorial analysis of variance. Scatter plot, scattergram, all those ones are your scores. The X is your hostility score. The Y is your anxiety score. You are the ones in there. What kind of correlation do you think that represents? Positive? Positive? Pretty high positive? Okay. The two concepts related to the distribution of these ones is homoscedasticity and heteroscedasticity. You know what those are? Homoscedasticity means that all the ones would be like in a pretty much a straight line like they are. Heteroscedasticity means that one half of them would be more like fan shaped. You'd have kind of a narrow, and then you'd have kind of a whole fan shape of ones up on top. Okay, so the distribution isn't the same all the way through when you have a heteroscedasticity kind of format. Probably more information than you want, but factor analysis is again using the correlation coefficient. I talked about that a little bit in terms of NBCC, and then doing factor analyses with this exam and the surveys. Likert scale, good for measuring attitudes, opinions, definitions. I don't think any of these are going to be real head scratchers. We've talked about some. We've you know most of those. Counseling program evaluation. Since about 10 years ago or so, NBCC's got a lot more concerned about programmatic evaluation, and evaluation of counseling programs has become very much in a bailiwick of what counselors do. Many of them do supervision and counseling, or they'll do administration and counseling, and they're in charge of counseling programs, development, evaluation. So this whole 35 section, and especially the evaluation piece about formative evaluation and summative, that's been on the exam. Don't overlook that for sure. Number 36, ethical issues in research. I think none of them are outstanding. Confidentiality, of course, you need to get permission, approval from folks. You can't just, record them or whatever without. Deception research is really kind of a scary, iffy sort of thing. It's not doable, assuming you have the right safeguards and then have an ability for people after they are deprogrammed or whatever to give them some services that they need. Finally, in that research human subjects committee, most institutions, universities, and so on that get federal money for research need to have institutional review boards or human subjects committees, and those are invaluable sets of folks in terms of analyzing your research design, looking for ethical issues, and so on. Finally, writing research. You write up your manuscript with your research results, you send it off to 5 different journals, and you kind of sit back and wait to see what happens. Is that right? One at a time. Every journal has panels of experts reading articles being sent in, and only one journal can publish your manuscript. So you send it to one at a time. If you send it to more than one at a time and they find out about that, you will never publish in those journals again in your life, probably. You wait till you get your first rejection, then you send it off to the next journal and then the next journal. This isn't Glamour magazine or whatever. You can send it to 5 different magazines and hope for the best, see who buys it, and so on. Let them worry about that. But it is in terms of professional writing and counseling and psychology. And that, my folks, is research. We're done with the tough stuff.